Okay, hi and welcome to Video Notes 8.8 Exponential Decay. Half-Life we'll save for the classroom notes so we can do that one together. But let's talk about exponential decay. First, before we talk too much about it, let's remind ourselves what exponential growth looks like. So here's exponential growth. Notice that in this model, or modeling, that we have a 100% of the ratio plus our rate. And we've talked about that. That's in notes. You'll notice decay then, what our difference is here, just starting off right fast and heavy, is that there's a subtraction between that. So we take what we call 100%, and then whatever our rate is, we subtract it off of there. And that looks a little bit odd, but that's where we get our exponential decay. Decay then has to have a growth factor, or a decay factor, we should say, that's got to be a decimal. Where with the growth, our growth factor had to be larger than 1. So if we're looking at this here, this had to be greater than 1. This one has to be between 1 and 0, and you can see that here. So to kind of explain that, we're going to jump down here for just a second, and I'm going to highlight it with a big asterisk here. It says that if you think of something decreasing by 5%, that the result then is really, it's kind of, I don't want to say it's growing, but it's 5% less than 100%. So we have to take that 100% of what originally was, subtract off the 5%, and then the result then is our factor, which is 95%. So it should always be less than 100% if it's a decay. So kind of getting that inside your head, we'll see some examples to see if we can explain that concept a little bit farther. But for now, what you need to know is that our B value, if it's a decay, meaning that it's decreasing each time an event happens. Remember, T is our events, or time periods, or whatever you want occurrences. So each set, our B value should be less than 100%, so it gets a little bit smaller. The farther it is from 100%, the more it drops, or the quicker that it drops, or decays. All right, but that's the main difference. It still looks like an exponential. We still have our initial value. We still have our events and our time, and this whole unit inside the parentheses, just like for the growth, is really your B value. Okay? So considering that, let's take a look a little bit closer at growth and decay. So if we've modeled a couple growth functions, a couple exponential growth functions so far, and we know that they have this nice steep curve to them, and they increase forever, and faster and faster and faster. And you can see, and I know it's tiny, but that B value there, 3/2, is greater than 1. And this one on the bottom is also greater than 1. And the tricky part about this, and what I want to talk about, is that growth can be negative. We can have a negative growth. Look at this function here. It's technically getting larger from left to right, which means it's growing. It just happens to be in the negative direction. So this is what we refer to as a negative growth. So let's just stop right there and comment on that. We don't want to get confused because it's going down. Some of us might think it's a decay, but what we really have to pay attention to is from left to right, as we read across here, because that's how we read our functions, right? From left to right, that both of these functions are getting larger. And what I mean by getting larger is our y values are getting larger. These on the bottom are getting larger in a negative fashion. These on the top are getting larger in a positive fashion. Hence our negative growth and our positive growth. But both are getting larger from left to right. So now if we stop and look at what a decay is, when we look at a decay, it still has that steep curve that mellows out and fans out to its asymptote. Can we say asymptote? Right? The boundary that it never crosses. And again, growth has one too. I didn't mark it before, but there it is. So the difference is it starts high, either in a positive side of things, and it decays lower, so it decreases from left to right, or it starts really, really low at a very negative number, and it comes in and it mellows out. But you'll notice that both of the decays are starting at a much higher value, and they get to a very small value. And that's kind of what happens with the decay. Isn't that what we're saying here? It should be shrinking by some percent as it goes. So when we talk about a decay, then it starts high and it goes low. So it decreases as you go from left to right. Okay, that's a great type of quiz question there. The comparison between an exponential growth, be it negative or positive, and an exponential decay, be it negative or positive. All right, so make sure you star that. You might want to do a simple little note of what we have here and add that to your back of your stamp sheet. It would be something great, something to add in there, something quick to pull out if you needed it. That would be something I'd throw on there. All right, with that being said, let's jump down and see it in action. So I've set this problem up a little bit for you already. We're comfortable enough that we know to start with our model for our homework. And on all of your homework, you should always start with the blank model. So you can see I've got my decay right here. So I've got that written out. Again, there's that subtraction from our 100% of whatever the rate is that it's decreasing in this situation. All right, so let's read through this. I know I got some lines in the way, but I'll read it for you. So it says, since 1980, the number of... Okay, so since 1980, the number of gallons of whole milk each person in the United States drinks each year has decreased. There's your first clue that this is a decay. It gives you a rate. I know it's hard to see with my line there, but it's a percent. Anytime you see percents, you should be thinking exponential. And this says decreasing at a rate, so you know it's a decay right away. Okay, so let's go ahead and label that R. You can see I've done that in advance. So our R is 4.1%. And we know we can't work with percents in our problem, so we're going to go ahead and change that right away to a decimal so that we can put it in there and calculate with it. So now we've got a rate. In 1980, each person drank an average of 16.5 gallons of whole milk per year. Notice how they're kind of setting us up here. They tell us something previous, and to me that indicates right away that it's our initial value. So our initial value A is going to be 16.5 gallons. We'll write that in right there. We've almost got every piece of information that we need for at least what the next part is going to ask us is. It says write an equation to model the gallons of whole milk drunk per person. So now we're set up. Notice it is just a model in this case, so no solving yet. The directions don't tell us to solve. They will down here, though, if you've been previewing. So let's go ahead and set up our equation. We're going to use our, let me change color here because this red's getting a little bit monotonous at this point, so we'll change to blue. So here's our base model. So we're going to plug each piece in there. We'll plug in A. B is that middle term. I wrote it out so you can kind of see it again, but really all we have to do is plug in our R value and subtract it from 1, and that'll be our B value in the middle here. And then T is what we would plug in to find out what our Y is. So to write in a model for an equation, we wouldn't actually put a value in there. So let's just quickly plug it in. Should only take a second, right? So our Y value is equal to, or our model is equal to 16.5 gallons times 1, our 100% of our original, minus our rate, which is 0.041 raised to the t. Okay, so let's clean it up so that it looks all correct and nice and neat. So y then will be equal to 16.5, and then 1 minus 0.041 is going to be 0.959 raised to the t power. So that's our model. Now the next question then is going to ask us to estimate or approximate how much milk is drank in the year 2000. So what they've really done here is they told us the number of periods or events, years in this case, that have passed of this decreasing value. So this decrease of 4.1%. So to get that then, we're going to take the original time, or this time, the year 2000, and minus it from the time that we started decreasing, or in our case, 1980. So if we subtract that off, we find out that our time period that we're measuring is 20 years. So all we're going to do is take our model, add in now our new input, which is t, and find out y, or how much it's decreased at 0.959% per year, or 4.1% decrease per year. So having that, we'll plug it in. So y equals 16.5 times our 9.59, and now we're going to raise it to our 20-year period. Hey, you know what? Let's pause. And I know you guys write in pencil, so this won't be a big deal. Let's change this to function notation. Again, when we put values in, I like to use function notation to show the input and then get the output, which is the whole f of x value. So now that we've got that, throw that in our calculator. going to pull it up here. I notice it's not opening right, so I'm going to open it up again, clear it out, and let's type that in. So here's our 16.5 gallons of milk consumed times our decay rate of 0.959. Again, I'm using parentheses, and I'm going to raise that to the power of 20, and it should tell me that after 20 years that our gallons of milk, whole milk drank per year is decreased to 7.14 gallons, or roughly 7 gallons. So in this case, we'll say roughly 7 because we're in a real world example. Now we're going to go ahead and write this in context. So we'll say something to the effect that the amount of whole milk consumed per year in the year 2000, not the best wording I've had, is 7 gallons. And that puts it in context. That's a decent amount of milk. If you look at 7 gallons versus 16.5 gallons, ask yourself this question: how much do you drink per week? Because you should be able to estimate that. And then when we get to class, let's talk about changing that to how much milk you drink per year. So if you want to go ahead and calculate how much milk you drink per year, great. But let's talk about that when we get back to class, because that's an interesting topic. Do you actually drink near 7 gallons of milk per year? Do you drink more? Do you drink less? Let's talk about that when we get back to class. You have no extra homework tonight except for to finish the work from class. If you didn't do that already, or finish your book work. So that will be the only thing that you have to do, because now you finished the notes and you should be excited. All right. So we'll see you when we get back to class, and we'll talk to you later.